Welcome to lesson number 3 in our nuclear chemistry unit. The previous unit we talked about the first observed instances of radiation, spontaneous radiation from an object, uranium salts. We then moved into talking about the quantities and qualities of the radiations that were produced by what we call decay. Now we want to go and look at the process of decay itself, and we want to do it quantitatively. First of all, notice the first term you see here is called natural transmutation. And when I say natural transmutation, that's going to be the same thing as natural decay. When a nucleus decays, we know it's undergoing a spontaneous reaction. Transmutation means a nuclear change. Whenever you see the word transmutation, immediately translate in your mind to nuclear change. Since it's a kind of an abstract word, not a very common word. The word natural, I think I mentioned a moment ago, that means a spontaneous change in the nucleus. Spontaneous change in the nucleus. And of course, the consequences I'll restate. Releasing radiation, and producing a new element. Both of these will be observed. Now I said in all decays, there are, or I should say, there is only one reactant. I'll point that out as we go. There's another kind of nuclear change that has two reactants, but that would not be what we call a spontaneous change. Okay, let's look at the first one, alpha decay. As I think might be obvious, an alpha particle is going to come into play here. Well, what happens in an alpha decay? Well, this is when, I'm going to say an unstable nucleus. Remember, this is decay, so we have to start off with something that's unstable. When an unstable nucleus emits an alpha particle. Now, it should make sense that if I'm getting rid of an alpha particle, the mass is going to decrease, and it's going to decrease by 4 atomic mass units. While, since I'm getting rid of an alpha particles consist of 2 protons, well, if I'm going to get rid of 2 protons, the atomic number has to decrease by 2. And I'll show you. It should be relatively easy to see. Now, if you notice, I'm missing a number. They don't always give you the bottom number of the element. Why? Because I can run over. If I run over to my periodic table on the wall, I can see that americium has an atomic number of 95. So be sure to write a 95 there. Now, what happens is this. The total mass on this side has to equal the total mass on this side. So if I start off with 241 units of mass here, then I have to have 4 plus this number to get that number. So that's going to mean that I'm going to have 237, a mass of 237 in the resulting nucleus, the new element that I promised you would be being produced. Downstairs it works the same. If I had 95 protons on this side, then I have 2 plus 93 on this side. Now, of course, don't stop there. To finish this off, you have to run back over to the periodic table and look up what element, and that's going to be neptunium. So notice, as I said, if you are what we call natural transmutation, you have only one reactant. You probably have only 2 products, but we're only looking at the number of reactants in order to identify this particular kind of nuclear change. Next one, beta decay. In a beta decay, well, it's going to involve a beta particle. It's going to involve that 0, -1b, or the 0, -1, right down at home, just slightly different, symbolized in a slightly different way. Well, in this one, again, it's when an unstable nucleus emits a beta particle. If you remember, I said a beta particle is the same exact thing as an electron, but that might confuse some of you, having accepted my statement that the nucleus only contains protons and neutrons, no electrons. How can I emit something that I don't have in the first place? Well, the answer is very, very interesting. This can happen because a proton, or I should say a neutron, turns in a proton. And it turns out when you do that, you have to emit an electron in the process. I'll show you exactly what happens. Well, if you're getting rid of a particle that has really no mass, then the mass is going to remain constant. So whatever we get over here as the new element is going to have really the same mass as what started. The atomic number, well, let's see what happens. Let's see that as a consequence of the math. Well, down here I have iodine 131. That's an unstable form of iodine. I need to run over to my periodic table and find its atomic number, since they weren't nice, they didn't list it for me. Actually, I do have to run over. 53. Mr. Sigelki has to check as well from time to time. Remember, there's only one reactant. We're producing, I don't have to, I could put the beta particle over here. I'm going to put it over here. That's what I normally do with it. 0, -1 beta. Let's do the math. 131 equals 0 plus 131. 53 equals -1 plus, careful, 54. Oh, take a look. The atomic number increases by 1. And the way we did that is by getting rid of an electron from the nucleus. Think of it this way. If you make your nucleus less negative by getting rid of an electron, you're making your nucleus more positive, and the only way you can do that is by turning a neutron to a proton. Now, don't stop here as well. I go over back to PT, and I see that's xenon. So this is an example of beta decay. Again, you can do it also in terms of the neutrons and protons. This is a neutron. If you look up on table O, that's the notation for a neutron. Now, if a neutron is turning into a proton, as I claim, let's see what the math tells us. 1 equals 1 plus 0, and 0 equals 1 plus -1. An electron. So in other words, when a neutron decays, and free neutrons will decay very shortly in space, it's got to decay into a proton and an electron. Very interesting. The third kind of decay, there are other kinds of natural decay, natural processes. We consider 3 of them. The third is what we would call positron emission. Yes, it's going to involve the positron. And you're already anticipating probably that, I'm going to probably write that in the first blank. Remember, this is the product side, and the first product I'm considering here is that positron. Now, if beta decay was emitting a beta particle, positron emission must mean that a nucleus, an unstable nucleus, is emitting a positron. Just as the positron is the opposite of an electron, the process that produces a positron is the reverse of the process that produces a beta particle. In this case, in the case of positron emission, it's a proton that's turning into a neutron. Actually, let me start with that first. If I had a proton in the nucleus, and that releases, or that, as I said, as I claim, turns into a neutron, well, what product must be produced? Well, let's see the math. 1 equals 1 plus 0, and 1 equals 0 plus 1. That is a positron. So if I had a proton decays into these two particles. Notice the mass is going to stay the same. The mass is constant again. But notice, since I'm losing a proton and it's becoming a neutron, that number is going to have to decrease, as you will see when we finish this decay equation for iron 53. Iron, we need to run over to our PT and see that it's 26. 53 equals 0 plus 53, again, no change in mass. 26 equals 1 plus 25. That was a decrease in the atomic number. And we go over to our periodic table, and we see that element number 25 is called manganese. Well, that was number 3. What we learned about today was writing these decay equations for something called natural transmutation. And I want you to know that whenever you see the word natural, that's referring to spontaneous decay. What we move on to next is a kind of nuclear change that is non-spontaneous, that has to be caused by a person, a scientist, or perhaps something massive like a star. I'll see you in the next lesson.